Hello, my friends, and welcome back to the Today Machine channel.
Role in car recycling.
Car balers play a critical role in the recycling process, as compacting ELVs saves space, reduces transportation costs, and makes metal recovery more efficient. Recycling ELVs is essential because it allows valuable metals, primarily steel, but also aluminum, copper, and other materials to re-enter the supply chain rather than being wasted. For context, about 75% of a car's total weight consists of metal, which is highly recyclable. With an estimated 12 to 15 million vehicles reaching the end of their life in the US alone each year, car balers are essential to processing this vast amount of material.
The baling process enables recycling facilities to transport large amounts of compressed cars to shredding plants, where further separation and sorting occur. By compressing vehicles, balers also contribute to cost savings in shipping.
Environmental impact.
The efficient use of car balers in recycling helps reduce the demand for virgin metal extraction, as recycled metal can substitute raw materials in manufacturing new products.
Aluminum.
How a car baler works.
Car balers typically consist of a large hydraulic press with substantial compressive force, often capable of producing between 125 and 200 tons of pressure. The baling process begins with operators placing an old car, often stripped of non-metallic parts, into the baler chamber. Once the car is inside, powerful hydraulic rams push from multiple directions, compressing the vehicle into a dense block of metal. In some advanced models, balers feature a continuous feed conveyor, allowing for more efficient handling of multiple vehicles in rapid succession.
Most car balers operate with hydraulic systems that apply force across several axes to ensure that the vehicle is thoroughly compressed. Some models are capable of processing an entire vehicle into a 3 by 3 foot cube, reducing the car's original size by up to 90%. This compression not only makes the vehicle easier to transport, but also prepares it for the next step in recycling, where it will be shredded or melted down.
Economic and industry benefits.
Using car balers helps streamline operations for recycling facilities, making them more profitable and efficient. For instance, processing a car into a bale not only saves on storage and shipping costs, but also allows facilities to handle a higher volume of vehicles. Additionally, the compressed bales are valuable to steel mills and foundries, which rely on this source of scrap metal for their own production processes.
The scale of old car recycling.
Worldwide, the automotive recycling industry processes millions of vehicles annually. In the United States alone, approximately 12 to 15 million vehicles reach end-of-life (EOL) status each year. The European Union sees about 6 to 7 million cars retired annually, while Japan processes close to 3.5 million vehicles. Collectively, these operations make the automotive recycling sector one of the most significant sources of ferrous scrap metal globally.
According to data from the Bureau of International Recycling, BIR, about 90% of a car's total weight is recoverable, with steel and iron comprising roughly 65 to 75% of a typical vehicle's mass. Given this composition, every scrap vehicle contributes approximately 1 ton of steel scrap, which is critical in steelmaking due to its high recyclability and cost-effectiveness compared to extracting virgin materials.
Role in steel production.
Scrap metal from recycled vehicles is instrumental in the steelmaking process, especially in electric arc furnace (EAF) steel production, which relies heavily on scrap metal. In the US, the steel industry used 76.7 million tons of scrap in 2020, with automotive recycling accounting for about 10 to 15% of that input. China's steel chain industry plays a pivotal role in the global steel market, exerting significant influence due to its scale, advanced manufacturing capabilities, and robust domestic demand. As the largest steel producer and consumer in the world, China's steel chain, encompassing everything from raw material acquisition to processing and finished products, impacts not only regional but also global economies. Comparing China's steel chain industry with the global industry reveals stark contrasts in scale, efficiency, sustainability, and recent developments.
China's dominance in steel production?
China produces over half of the world's steel. In 2022, China's crude steel production was about 1.01 billion metric tons, representing more than 53% of global output. In comparison, the second largest producer, India, generated approximately 125 million metric tons, and the United States produced around 80 million metric tons. This overwhelming production capacity allows China to meet its significant domestic demand while exporting to global markets. Chinese steel exports stood at roughly 67.3 million metric tons in 2022, positioning China as a key player in the international steel supply chain despite its export decline in recent years due to increased internal demand and environmental pressures.
Vertical integration and efficiency.
China's steel industry is highly vertically integrated, which gives it an edge in efficiency over many other global players. From mining iron ore and coking coal to producing pig iron and processing crude steel, Chinese companies manage a complex supply chain that integrates multiple stages of steel production. This structure helps reduce costs, improve coordination, and ensure a steady supply of raw materials. Companies such as Baowu Steel Group and Ansteel are among the largest and most efficient in the world, thanks to their high degree of integration and investment in advanced technologies.
In contrast, many steel producers outside of China are less integrated, often relying on separate entities for mining and raw material processing. This segmentation can lead to inefficiencies and increased costs, particularly in regions with less favorable access to raw materials like the European Union. In 2022, the European steel sector produced around 136 million metric tons of steel, far below China's production and with higher average production costs.
Innovation and advanced technologies.
Chinese steel manufacturers invest heavily in research and development, focusing on digital technologies and automation to enhance production efficiency and quality. China is a leader in smart manufacturing within the steel sector, utilizing AI-driven data analytics, robotics, and the Internet of Things, IoT, to streamline processes and improve yields. As a result, China's steel mills have made significant strides in productivity, achieving production rates of over 1,000 tons per employee annually in top-tier facilities, significantly higher than the global average. EAFs can produce steel with up to 90 to 100% recycled content, making them a key driver of circularity in the industry. The steel from recycled cars maintains the same properties as steel from raw iron ore, enabling manufacturers to meet the same quality and durability standards without new mining activities. In this sense, the old car recycling industry directly contributes to the 1.7 billion tons of steel produced annually worldwide by making up an essential part of the material input for EAF processes.
Environmental benefits of car recycling for the steel industry.
Steelmaking is energy intensive and resource demanding, and using recycled steel provides substantial environmental advantages. Recycling steel from EOL vehicles reduces energy consumption by about 74% compared to producing steel from iron ore. The World Steel Association estimates that each ton of recycled steel saves 1,115 kilograms of iron ore, 625 kilograms of coal, and 53 kilograms of limestone. Consequently, each ton of steel scrap used can avoid approximately 1.5 tons of carbon dioxide emissions.
The automotive recycling industry in the US alone reduces carbon dioxide emissions by about 12 million tons per year. In Europe, automotive recycling is estimated to cut carbon dioxide emissions by around 8 million tons annually. In terms of water savings, recycling steel conserves approximately 40% of the water needed for steel production, further reducing the environmental footprint of steel manufacturing. Economic impact and job creation.
The automotive recycling industry generates significant economic activity. In the U.S., it contributes over $25 billion to the GDP and sustains around 140,000 jobs. Europe's automotive recycling sector, valued at approximately 8 billion euros, supports over 70,000 jobs across various stages, from dismantling to transportation and resale of recovered materials. Process of recycling cars for steel.
Automotive recycling involves several stages, each designed to maximize the recovery of valuable materials. After a vehicle is decommissioned, it undergoes depollution, where hazardous fluids such as fuel, oil, and brake fluid are safely removed and processed.
Once stripped of reusable components, the car body is shredded into smaller pieces. This shredding process allows for easier separation of ferrous metals, steel and iron, from non-ferrous metals and other materials, such as plastic, rubber, and glass. Afterward, magnetic separators are used to extract ferrous metals, which are then collected and shipped to steel mills or foundries for remelting.
In many countries, automotive shredding operations adhere to strict regulations regarding recycling rates and material recovery. The European Union mandates a 95% recycling and recovery rate for vehicles, including an 85% material recycling rate.
Challenges and innovations in automotive steel recycling.
While the automotive recycling industry is highly efficient, it faces challenges due to the increasing use of lightweight materials like aluminum, magnesium, and carbon fiber in vehicle manufacturing. These materials are less valuable to the steel recycling process and require separate handling, complicating recycling operations.
To address these issues, the industry has seen innovations in dismantling and material sorting technology. Advanced shredders and optical sorting systems have become more common, enabling recyclers to identify and separate various metals with higher precision. Research into automated dismantling systems, including robotics, is also underway to improve efficiency in deconstructing EOL vehicles. future of car recycling in the steel industry?
The role of automotive recycling in the steel industry is expected to expand as global demand for sustainable materials increases. The push for a circular economy, in which materials are reused and repurposed, underscores the importance of maximizing the recovery of steel and other metals from discarded vehicles. Steelmakers, for their part, are increasingly aligning with these sustainability goals by enhancing their EAF capacities and investing in more efficient scrap processing technologies. Environmental pressures and sustainability efforts.
Environmental concerns shape the steel industry worldwide, and China is no exception. With the Chinese government aiming for carbon neutrality by 2060, the steel sector is under immense pressure to reduce its carbon footprint. In 2021, China's steel industry emitted approximately 1.9 billion metric tons of CO2, accounting for around 15% of the country's total carbon emissions. In response, many Chinese steelmakers are increasingly investing in cleaner technologies such as electric arc furnaces, EAF, which have lower emissions compared to traditional blast furnaces. However, EAFs currently represent only about 10% of China's steel production, far lower than the global average of 28%.
In comparison, regions like Europe and Japan have adopted more stringent environmental regulations and have higher EAF usage rates, around 41% and 24% respectively. European steelmakers are also investing in hydrogen-based production methods as a sustainable alternative to coking coal.
Economic and geopolitical implications.
China's steel industry is closely tied to its domestic economy and has significant influence on global trade. The steel sector directly employs millions of Chinese workers, and related industries such as construction, machinery, and automotive rely heavily on affordable steel.
To reduce dependency on China.
Future outlook and global influence.
The future of China's steel chain industry will largely depend on its ability to balance economic growth, sustainability goals, and global market integration. As urbanization continues within China, domestic demand for steel remains strong, particularly in construction and infrastructure development. The process begins with the McGriot lifter, a lifting device that moves steel plates onto the line. Once in place, the edge milling machine preps the plate edges by removing any impurities and creating a clean, smooth edge to facilitate high-quality welding later in the process. After edge milling, the plate proceeds to the pre-bender machine, which preforms the steel plate, initiating the first bending operations to start shaking it into a pipe.
Next, the plate moves into the infeeder machine, which ensures accurate positioning and guides it into the JCO press bending machine. Here, the machine applies sequential bending, known as the JCO process, where the plate is bent in the shape of AJ, then C, and finally an O, achieving the cylindrical shape of the pipe. This press bending machine forms the core of the production line, shaping the steel precisely to meet the desired specifications.
Once bent, the pipe is transferred by the turning transfer car to the tack welding machine, which performs an initial tack weld along the seam to hold the pipe's shape before final welding. The pipe then undergoes 2 stages of welding, inside welding for the inner seam and outside welding for the exterior. Between these, the back bead cutting machine removes any excess metal from the inner weld bead, ensuring a smooth, uniform finish.
After welding, the pipe moves to the four-way machine, impending machine, which further refines its structure and prepares it for final operations. The end-facing machine then machines the pipe ends, creating smooth, even edges that meet industry standards. A washing device cleans the pipe to remove any residual metal debris or oil.
Next, the X-ray test machine scans the pipe for structural integrity, detecting any internal flaws that may require repair. Passing inspection, the pipe proceeds along a turning conveyor for further processing. A varnish coating machine then applies a protective coating to the pipe, enhancing its durability and resistance to corrosion.
Finally, the coated pipe is directed to the outgoing pipe station, where it is prepared for packaging and shipment to customers. This entire line ensures a seamless, efficient production process, producing high-quality steel pipes that meet stringent industry standards. The CNC rod bending machine automates the bending of metal rods into precise shapes and angles, controlled by computer programming. The process begins with feeding a rod, typically metal, into the machine, where it passes through rollers or feeding mechanisms that align and position it accurately. CNC computer numerical control systems control every aspect of the machine's movements, allowed for high precision and repeatability.
Once the rod is positioned, bending tools engage to shape it into the desired form. The primary bending mechanism is a rotary or mandrel system that wraps the rod around a bending die or mandrel. This mechanism allows for multiple bending radii and angles, often in complex 3D geometries. The CNC programming enables the machine to control not only the angle of each bend, but also the spacing and positioning along the rod, resulting in complex designs achieved without manual intervention.
Some advanced CNC rod bending machines also include automatic feeding, cutting, and ejection systems, streamlining production for continuous or batch processing. The machine software is typically programmed with CAD data or custom inputs, allowing operators to quickly adjust designs and switch between parts.
The CNC system minimizes human error and reduces waste, as every bend is executed with precision and consistency. This technology is especially useful in industries like automotive, construction, and furniture manufacturing, where precise rod shaping is essential for structural integrity, aesthetics, and functionality. The process begins with an automatic material feeding machine, which ensures that raw materials are fed seamlessly into the system. The material then goes through a 360 degrees raw material straightening machine, which corrects any deviations and aligns the material for precise cutting and shaping. An aggregate conveyor transports the straightened material along the line to the crocodile-type hydraulic cutting machine, where it is accurately cut to size.
After cutting, the material proceeds to a numerically controlled sizing unit, ensuring each piece meets exact specifications before entering the hydraulic bevel angle putting machine, which prepares the material for further forming. The processed material then enters number 1 automatic production line, where it's sent to a combined hydraulic necking machine, which reduces the diameter of the bolt head area, shaping it for threading.
Next, the hydraulic thread rolling machine forms the threads on the bolt. For bolts requiring nuts, they pass through a nut screening machine, which inspects each nut for quality before it reaches the automatic screw machine for combined nuts. Tamping nut bolts, non-planting type, are directly transferred to the next station for further processing.
A full automatic punch-in and pin machine then prepares the bolts for the final stages. Here, a strapping and finishing machine ensures all bolts are bundled neatly, followed by an automatic steel strapping machine that provides additional reinforcement. The line concludes with a CNC stack crane, which organizes and stacks the completed bolts for efficient handling and storage.
Each component in this fully automated production line is carefully synchronized, creating a smooth, high-speed production flow that maximizes efficiency, precision, and quality in manufacturing round steel bolts. This automated setup reduces labor requirements, minimizes error, and supports high output, meeting the demands of modern industrial applications. This fully automated line can handle various bolt types, including screw-thread steel bolts, thanks to its versatile electric, hydraulic, pneumatic, and automation control systems.
The process begins with raw material feeding, where steel rods or wires are loaded onto the line. First, the raw material passes through a 360 degrees raw material straightening machine, which ensures straight, uniform material for consistent bolt production. After straightening, the material moves along an aggregate conveyor to the next stage.
At the numerically controlled sizing station, each piece is cut to precise lengths, ensuring every bolt meets the required specifications. The cut material then reaches a combined type hydraulic necking machine, which shapes the bolt head by reducing the diameter of one end. This step prepares the material for threading and further processing.
Next, the hydraulic thread rolling machine forms the screw threads along the bolt shaft, achieving the desired thread pitch and depth through controlled pressure. Following thread rolling, the bolts enter a combined type spinning and impact extrusion machine, which adds additional shaping or reinforcement where needed.
For enhanced strength and surface finish, the bolts then pass through a cold rolling mill. The bolts are then transported to an automatic point welding machine where any required welding operations are performed with precision. At the twist machine, specific twisting or contouring is added to meet custom specifications if necessary.
Bolts needing nuts then proceed to the automatic screw machine for combined nuts, where nuts are attached or assembled as required. The bolts advance to a full automatic punching and pin machine, preparing them for final packaging.
In the final stages, the bolts are organized by a strapping and finishing machine and secured with an automatic steel strapping machine. Finally, the CNC stack crane collects and organizes the completed bolts into stacks for efficient handling, storage, or shipment.
This fully automated production line allows for the high-quality, high-volume manufacture of screw-thread steel bolts, meeting diverse industry requirements while maintaining high precision and reliability in each step. Ferrous scrap processing. Ferrous scrap undergoes mechanical treatment for size reduction, weighing, and storage. The scrap is then organized into baskets for easy transport and handling with overhead cranes, which then feed it into the furnace.
Coal and lime processing. Coal and lime are weighed and transported to the furnace, where they contribute to the melting and refining processes.
Electrodes and refractory handling. Electrodes and refractory materials are weighed and added to the furnace to maintain the necessary high temperatures and protect the furnace lining.
Material handling and transport.
Raw materials arrive by train or truck and are managed using in-house transportation equipment such as wheel loaders and trucks. Finished products are transported with forklifts, while waste materials are taken to dedicated disposal facilities.
Melting process.
In this phase, an electric arc furnace, EAF, melts the ferrous scrap, pig iron, and other inputs. Oxygen is produced to aid in the combustion process, and cooling water is circulated to prevent overheating.
Secondary metallurgy.
Once the metal is in molten form, it undergoes secondary metallurgy, which refines the steel's composition. This step includes adding ferroalloys and other additives, as well as weighing and sending materials to a secondary furnace. Here, ladles, large containers for transporting molten steel, are prepared and maintained to ensure proper steel handling.
Casting process.
The casting phase transforms the refined molten steel into billets, which are long rectangular bars. This involves preparing tundishes, holding containers, to control the flow of steel as it moves into casting molds, forming the billets. After casting, the billets are allowed to cool and solidify.
Billet preheating and surface preparation.
The billets are preheated in a furnace to soften the material and make it easier to work with.
Hot rolling process.
Once preheated, billets are transferred to the rolling mill for the hot rolling process, which gradually addition the billet to the desired wire rod diameter. Bettini Group, known for its expertise, produces wire rods in diameters ranging from 5.5 to 21.5 millimeters for smooth rods and 6 to 16 millimeters for rig rods.
Quality control and finishing.
After rolling, the wire rod is carefully inspected to meet quality standards.
Waste management and recycling.
Throughout the process, waste materials, including slag and refractory remnants, are removed and either recycled or transported to waste facilities.